So good evening. I will start today's session. So yeah, you can go ahead and ask the topic.
Sir, the doubt is that for applying that RTT linear momentum principle,
Hmm.
suppose we choose a control volume such that which cuts through a solid for some portion and is surrounded by fluid for the rest of the portion.
Okay.
And suppose the surface force which is exerted on the contents of the control volume by that fluid portion is atmospheric pressure everywhere,
Okay.
but then the surface force which is exerted by the solid portion, that we do not know.
Okay.
Yet in some problems in books I have found that yet they are saying that this control volume is surrounded by atmospheric pressure everywhere, and so net effect gets cancelled.
Okay.
For example, for your convenience, if I share a screen.
Yes, sure. You can. I think like while sharing my screen, also you can share the screen, right?
Okay, sir.
Mhm.
1 minute. Uh, Sir, is it visible?
Yes.
Sir, here is a problem of a horizontal jet of water which exits a nozzle. It strikes a vein and is turned through an angle theta. And the vein is actually kept stationary, and it is asked to find that force needed to hold that vein stationary. Here
Mhm.
the control volume has been chosen like that. You can see by these dotted lines.
Yes.
So the in the that lower portion it cuts through that solid, that vein, and in the rest of the portion it is surrounded by fluid.
Okay. If I understand your question, like your question is why in the solid portion, like uh, the atmospheric pressure has been assumed in the solid uh, portion as well, right?
Yes,
That's
sir.
what.
Here it explains that the water enters and leaves the control volume as a free jet at atmospheric pressure. Hence, there is atmospheric pressure surrounding the entire control volume, and the net pressure force on the control surface is zero. Here it says.
Hmm.
So,
Yeah.
how can we conclude that in the that solid portion, the atmospheric pressure is being exerted? We do not know what forces are there.
So in this case, the solid is fixed, right? The solid is
Yes, sir.
fixed. It's not moving. Hmm. So, so in this case, uh, so let me share my screen. I have understood your doubt.
Okay, sir.
Yeah.
Uh,
So you are saying like let's say some water jet is flowing, and let's say it's changing its direction. Why is it changing its direction? Because it's in contact with the solid surface, right? It's in contact with the solid surface. It's changing its direction. Now, what we do in this kind of situations is generally we use our Reynolds transport theorem, define a control volume, and then apply our conservation of mass and momentum to find out uh, the dynamics of this kind of jet. And so we can choose a control volume like this. Okay. So if like which surrounds only this jet. So there will be atmospheric pressure, and that atmospheric pressure, like as you are correctly saying that in these surfaces we definitely know atmospheric pressure is also acting, along with any other forces that might be acting. Right?
yes, sir.
It is true for the solid itself also. So even if you take a section of solid, then also there will be definitely other forces that are acting because this water jet is hitting it and it's changing direction, but atmospheric the atmospheric pressure here is also acting. Okay. uh, so like to say this more convincingly, let's say that like this is the section you have taken. So it cuts some amount of solid. Hmm. Now, if you take some other section like this, so this solid is fixed. Hmm. So let's take some other section. So here also you will see that since the solid is not moving, the balance of all the forces must cancel, right?
Yes, sir.
Hmm. So here also the atmospheric pressure will definitely be there. So all the forces that is this jet is means let's take the solid, part of the solid. So on this solid, the force this uh, jet is applying some force, and this force is getting transmitted through a shear force on the other side. So this the rest of the solid that at the bottom where it is fixed, this will apply some amount of shear. Hmm. So and the other portions will have some atmospheric pressures. Those are balancing each other. So in like you have your means inside your jet also you are like saying that there is a gauge pressure and the atmospheric pressure. Here also inside the solid also there is an atmospheric pressure as well as the other forces, other surface forces which are present. Okay.
So,
Hmm.
sir, according to you, so if suppose there wasn't any jet of water flowing through that vein, and
Yes.
in that case, if we have chosen such a control volume through
Hmm.
it, and then also we would have concluded that solid atmospheric pressure is still acting. I mean, through that cut portion of the solid.
Yes. That's definitely the case. Hmm.
If I'm not considering the weight, right?
The weight of what? Sorry.
The weight of
The
that
weight of the solid
vein.
portion. Okay. Yeah.
Yes, because
Mhm.
then the force balance will say something else.
Mhm. Definitely. The atmospheric pressure component is also there.
So while solving such problems, if I choose my control volume which cuts through a solid portion, then I have to assume that yes, in that solid portion as well, I have to give that atmospheric pressure
Atmospheric
acting.
pressure. Hmm. So basically, this atmospheric pressure will means, cancel out.
Okay, fine, sir. Got it.
We will like today in our assignments problems very similar to these are only there. So we will be extensively solving these problems. Okay. I think like that will make it more and more clear as we solve through this. So yeah, in this first problem itself, there is a jet of water and it's splitting into two due to contact with the solid surface. So here also, what we will do is basically first mark the control volume. So what will be the control volume? Let's say like somewhere here, where it is means this is the end of the inlet portion, and you can follow any path like along the jet, just making sure that there is the jet is inside this control volume, and we'll make one cut at this exit, and here also we will make one cut at this exit, and we will join it along the surface. So if you have like any like problem with cutting through the solid, you can always assume that you are cutting along the interface between the solid and the fluid. Hmm. That way you don't have to like means have the dilemma whether the solid is like if I am cutting inside the solid, then what is happening? So if you are cutting inside the solid, the stresses inside the solid will come into play. But if you are cutting
Yes.
along the interface, then only the forces that are exchanging between the solid and the fluid is you are considering. And in that case, the atmospheric pressure is definitely there because like in that interface, one side is the fluid, which is definitely applying the atmospheric pressure along with any gauge pressures that are present and the shear stresses. And thus, since it is a surface force, and we know the Newton's third law, the solid is also applying the same forces back to the fluid. So if you take your control volume along the interface between the fluid and the solid, then these doubts disappear. then you are very sure that atmospheric pressure component is also present, right?
Yes, sir.
Hmm. Okay. So yeah, um, this is our control volume. We can uh, in in these curved edges, the curved edges there is no force transfer as such. Like atmospheric pressure is present throughout, and atmospheric pressure will cancel out. So what we are more interested in? We are interested in this inlet. Let's take this as surface one. These outlets. This is let's say this is surface 2, this is surface 3, and also this interface between the solid and the wall. Why? Because here also some force application is definitely taking place. Hmm. So this is 4. Okay, all right. Now what we have to do is we have to develop an expression for this H2 by H. So H2 is the top portion, this width of the jet of the top portion, and H is basically the inlet. And uh, so here they have mentioned that the flow that is taking place along the plate, this is the frictionless flow. So frictionless flow, that means there is no tangential force on the plate surface. So whatever forces is exchanged between the fluid and the solid is normal forces. So which is the atmospheric pressure plus the gauge pressures, whatever the gauge pressure. So what does this give? This assumption gives me, it gives me the direction of the force along which this force that is exchanged along this surface 4 is taking place. So along the surface 4, the only force that is acting is in this direction, right? Now, do I know the value of this force? I do not know the value of this force. So then do I need the value of this force? I do not really need the value of the force like to find this expression. What I will do, I will basically solve the momentum along the perpendicular direction to this force. Then I do not have to think about this particular force. Okay. So you will have two equations. One is the mass conservation equation, RTT for two things. One is mass conservation. Hmm. So the velocities are provided. The speed is constant for all these inlets and outlets. So with mass conservation, you will get a relation which relates H2, and H3. So these three are related through this mass conservation equation. And to get my final expression for H2 by H, I need to eliminate the H3. How I will do that? Using my momentum conservation. Momentum conservation. Along which direction? Along this perpendicular, along this plate basically. So perpendicular to this force. So let's call this like y direction. So this is y direction. Now, along this y direction, you will find out uh, the you will do the momentum conservation. So there is no external forces acting. So only the RTT, the forces due to the flux in and flux out, those things will be there. Even the temporal term will not be there because this is steady. Inside this control volume, whichever point you look, it is not changing with time. So nothing is changing with time. Uh, so there will be no temporal term. There will only be the flux term. Can you attempt to solve this problem? Yeah, you may speak. You can unmute and speak. So let's do one thing. Let's write our Reynolds transport theorem for mass conservation. So along the control volume, my del rho del t, this this is my temporal change inside my control volume plus along the surface of the control volume. You can do this, or I can write a. This is my flux along the surface of my control volume. This is equal to 0 if there is no mass generation or mass consumption terms. So this is my Reynolds transport theorem on the control volume. So this, what is my first term saying? My first term saying is what is the change of density inside my control volume with time? Is there any change of density? There is no such a thing. Like it is in a steady state, so nothing is changing inside my control volume with time. So this component is 0 here. This component is 0. Now, is my mass coming out or means going in or coming out from surfaces? So that is definitely happening. So which surfaces are important in this case? In this case, my 1, 2, and 3, these three first surfaces are important, and I have to write down this term for each and every one of these surfaces. So surface 1, for surface 1, it is coming inside. So for like a mass which is coming inside, we will use the negative sign because the flux is inwards. So rho v is the velocity, velocity which is normal to my control volume. So I have drawn a normal surface. So if I drew a tilted surface which will just make my life more difficult, if I suppose cut it not perpendicularly but at an angle, what would happen? I will take the component of my velocity, but that would not change the physics of it because I will also take a component of the area. So the area will be more, the velocity will be less, and it will be different by multiplication of the cosine of the angle, and they will cancel each other out, and I will get my same result. So this is just I have taken a perpendicular to simplify the problem. It is physics won't change if I don't take a perpendicular constant. That was I was trying to say. Yeah, and this area is basically h into whatever unit width is there. So this is a 2D flux. A unit width will be there. I am assuming a unit width, so I am not writing width everywhere. So I am writing is as h. Whatever 2 and 3, similarly I will get this is h2 and this is h3. So I will get expression. This is for my conservation of mass. Right. So similarly, I can also perform my conservation of momentum. So momentum I am doing in the y direction because in my x direction this force F is there, which is unknown, and this unknown force I don't want to put it in my equations because then I don't want to solve for this unknown force. I don't need this value. So I will just ignore this and uh, like solve my conservation momentum conservation in a perpendicular direction. So if I take that, so here also my Reynolds transport theorem I can write down for momentum. So y momentum, dy left. This is my momentum. This is equal to whatever the forces, the external forces that are applied. So external forces in this direction. So in the y direction, external forces in the y direction will be 0. It is 0, and this will not be affected because I am going on the y map. This this force is 0. So this is equal to 0. This is equal to 0. Just a similar reason to our like conservation of mass. Nothing is changing with time inside my control volume. All at every point my velocity remains same. So this uh, time derivative, time partial derivative, this will definitely be 0. I again need to solve only this term. So here which surfaces are important? 1, 2 and 3. Why 4 is not important? 4 is not important because the surface is, the flow is frictionless and there is no tangential force. This is already given. That's why I can like do this simplification and ignore my uh, sur- fourth surface, which is the surface with the solid. So here I can again like do this. So uh, for surface one, again this is coming in. So the momentum is coming inside. So this is a negative sign. Flux is inwards. Okay. Uh, Rho Vy is there. So for Vy, I need to find the y direction component. Hmm. So this is my v velocity in my inlet. I need to find y direction component. Y direction is this direction. Hmm. Okay. So for that, this angle is already given theta. So what will be this component? Can someone tell? What will be the y directional component? You can unmute and speak. And
Sine theta.
yeah, huh?
V sine theta.
So this will be v sin. Definitely. So, v sin theta. So so vy instead of vy, I will put v sin theta here, and this v dot n is minus v. So this is v square. And similarly, I can do for option two and option three. Okay, area I have not mentioned. So area will be h. Unit width. So h. Uh, so similarly for two and surface three, uh, we'll do the same. So here Vy is positive V. So V will be there, and this is in the outward direction. So this will also be positive V. So V square. This is H2. Here for surface three, this is rho. Vy in this case is negative direction. So this will be minus V. V dot n is again positive V. So this will remain minus. So V square and H. This is equal to 0. So I need to substitute H3 from here. So H3, this is equal to H minus H2. I can substitute. Can you tell me how much my H by what is last? H2 by H. Okay, so H2 by H. Find the expression from it. Please let me know the answer. So you can substitute H3. You can substitute this. Hello. Does anyone want to like say something? You can unmute your mic and speak. It's no problem. So if you substitute H3 here, you will get this is H minus H2. You can take all the H terms the other side, and H2 terms can remain this side. Then you will get this 1 plus sine theta. You can solve this very easily. Like if you just instead of H3 write this and separate out the terms, you should get this. Yeah, this is the correct answer. Is there any question regarding this? You can ask. There is no problem. If you have any question regarding how this problem has been solved, okay, we go to the next question. So a small round object is tested in a uh, 0.75 diameter wind tunnel. The pressure is uniform across the sections 1 and 2. Okay. The upstream pressure is 30 mm H2O and the downstream pressure is 15 mm H2. Okay. So pressures at this P1 and P2 these are given. P1 is given, P2 is given. In terms of this. So you can find the pressure like using density of water. You can definitely find the pressure. Mean airspeed is given as this. Uh, the velocity profile at section 2 is linear. It varies from 0 at the tunnel center line to a maximum at the tunnel wall. The maximum velocity in section 2 is asked. Okay. So mean airspeed is given as this. So this is what is like present here in at the inlet. So at the inlet, it is the pressure, the velocity v is given here as 12.5. So what we have to do is basically find this v max here. The pressure profile is being given. So what we can do is simply again define a control volume. define a control volume like this, and use our conservation of mass to find out the velocity. So since there will be no fluid accumulating or like there will be no consumption of material or like release of any mass, so mass will the inlet mass and the outlet mass will be same. So we can like use that principle to solve this question. So now we can again name our surfaces like this. Let's say inlet surface I can name 1, and this is 2. It's already given here. And let the walls be 3. Are we concerned about the walls? We are not concerned about the walls. We are only concerned about 1 and 2. So if I write our, let's use the next. Yeah. So write RTT. This will simply boil down to rho d cap dA. This is equal to 0, and this will be simply for my first surface and second surface. Now surface 1 is pretty simple. So surface 1, rho is definitely constant, it's coming out, and v dot n is v here is constant, which is capital V. It's given, and dot n means like since it is going inwards, so the dot product will be negative here, so a minus sign will come out, and I have v, and this dA is there, so dA is the integration dA will be the area. So the area here like has not been given. So let us assume that this area means this is the 2D profile, and the like area is some h into w. Yeah. So the area is h into w. So can have this as our area, and for the second problem, we can take the row out. We can also take our width out because we have assumed it as a 2D profile. So nothing is changing like across my plane. And regarding the velocity, so this velocity is a linearly varying velocity which has a maximum at its edges, and uh, at the center line the velocity becomes 0. Hmm. So what we have to basically do right now is find this v into dy, uh, v dy integration, and this v function here is linear till center line and again linear. Now, since because of this symmetry, I can simply write this as 2 into 0 to h by 2 y dy. So at h by 2, like I am taking this as 0, and this is h by 2. So this is the maximum limit. So this will be y dy. So this is linearly varying at h by 2. This is v max. So I will simply normalize it like this, h by 2, and put v max. You can see this is a linear function. So I have just simply written the slope here. So v max is the value that I will get when y becomes h by 2, and you can put y is equal to h by 2 and see that this is coming out to be v max. If you have any question regarding how like this have like you can ask. Or like any other question. So we have to integrate this. So let me like write this down here. So let me write this down here. So, yeah, w and rho we had taken out. This would have been vy dy. So vy we have the expression. is a 2 upstairs and h by 2 down. So this will be 4 Vm by h y. This is equal to 0. And this is pretty simple, straightforward problem to solve. Rho and W cancels out because it's there in both the terms. So if we do this, and this is from 0 to h by 2. This integration is from 0 to h by 2. So 4v max by h multiplied with this integration. So this integration, this will be y square by 2. So if I put y square here, it will be h square by 4. So this is h square by 4 by 2. So h square by 8. And this is equal to v into h. This v is the inlet velocity that is given. But we have to find out this Vmax. So this Vmax will be Q into V. So it's already given 12.5. Okay, I think like we also okay. Just a second. Here, okay. Since the pressure difference is given, I think like we have to take into account uh, that. So pressure velocity profile is at section 2 is given. So what we have not done here is basically we have not we have used the continuity equation, and from continuity equation we will definitely get a value of this Vmax if this profile is given. Hmm. But like from reading this, what I understand is that this is not a 2D profile. So what we have assumed is a 2D velocity profile. So there is no like uh, velocities like spillage as such. So what they want to test is like using this pressure, uh, we can also apply the Reynolds transport theorem for conservation of momentum. So we can definitely we can do that. For conservation of momentum, we will integrate along the these edges. So, this is with my force. So this is equated with my force. So this is the change in momentum, and it is equated with my force. So the temporal term will not be there because there is no like variation, a temporal variation inside my domain with respect to time. So this is equated with my force. This force arises due to the pressure difference. So force arises due to the pressure difference. So we are taking this as positive x, and this we can simply we can write it down accordingly. So here instead of like taking we will take this linear profile itself. but instead of integrating v dy, we will integrate v square dy. So this will be integrated uh, because two v's will be there. For the surface one, we can again take v constant and take it out. And uh, for force, we can simply take this uh, force along x, so p1 minus p2 into the area. Using this, we can calculate our Vmax. So here the Vmax expression will be there. Uh, yeah, so this actually the problem with this is our cancelling of the density. So the density term might actually change. So I had not like noticed that before. Like since we are dealing with air here, hmm, so I had not noticed that. So the density of the air might change because of this variation in pressure. So we will not be able to cancel out the like densities like this. So instead of using conservation of mass, here we will actually have to use our conservation of momentum. So I'm not solving this again. From here you can find out like Gmax. If you have any problem, like you can like, unmute and ask. Yes. So instead of like conservation of mass, we will use conservation of momentum here because the density variation we do not know. We do not know my rho one and uh, like rho two, and this won't be equal. They will be different. Okay, that's why we will get different answers if we do with like mass conservation or momentum conservation. Let's move to the like, next question. So this next question is referring to the previous problem itself. So we'll draw the previous figure. So here is the ball, and here inlet velocity is given as like this is the uniform velocity here. V. And at outlet, there is a variation in the velocity field, and at the edges, the velocity field is maximum, and uh, at the center, it is zero. So it's V max here, V here. So what we have to do is find out the drag of the object and its supporting them. So like can you say how we can we approach this problem? So in the previous problem, we had actually included this inside our control volume, and we were only focused on this the two outer edges. And using these two outer edges, the velocity profile there, we had found out our Vmax. What will be the change in our velocity? Now, in this question, the drag on the this object, this is being asked. It will be very helpful if you solve this problem with me. Then, like, if I am doing any algebraic mistake, then like we can both figure it out quickly and like proceed with the concepts, exploring the concepts of the problem instead of like doing the algebra. So what I feel is that I have done some algebraic mistake while solving the previous problem. So that is what was leading me to the wrong answer, like not uh, the pressure one. So what I feel is like let's see, let's recheck my question too, and come to the next question. It will be helpful if you do it do it as well.
Sir, shall we
Yeah.
find the velocity profile and based on that, shall we solve the problem, sir? First, we will find out what is the velocity profile.
Mm-hmm.
Yes, sir.
Yeah. Uh,
Uh,
so the outlet velocity profile here is given already. So based on this, we will need to solve this problem.
yes. Uh,
Yeah.
so it is given as it is linear. However, what is that um, uh, profile? Actually, that is not. It varies from zero at the tunnel center line to a maximum. It is given, sir,
Yes.
at the tunnel wall. So if we know the profile, we can integrate it, no, sir?
Yes, we can. If we know the profile, then we can definitely integrate it. So,
Yes, sir.
uh, if the profile here is given as such that this at the center, this is 0. Hmm. So let's take this as y direction. So at this edge, this y is h by 2, and at the
Yes, sir.
bottom edge, this is minus h by 2.
Yes, sir.
And at the bottom edge, my velocity is vmax, and again at the top edge is also its vmax. So we can integrate it directly. uh, this is linear, so this will form two triangles, so we can definitely integrate this directly. So if I want to find v dy, then I can integrate this, or I can do another thing. We know that like integration is area under the curve. So this will basically be the area of these two triangles, that is there, right? So
Yes, sir.
uh, so here the edge of this triangle is vmax. This edge is h by 2, and my area of the triangle is half into Vmax into h by 2. Since there are two triangles, I can multiply it by 2. So the this v integration v dy, this will be v max into h by 2. So had I done this correctly here? So rho I had taken out, w I had taken out, uh, h was there, another h was there, and so v dy would have been uh, after rho w, v dy would have been there. So rho w had cancelled. So here I had got v max into h by 2. It is correct. So what I am getting as my answer here is actually v max is equal to 2v. So my problem here is becoming that here the mean airspeed is given as this 12.5 meter per second, but what I am getting as my v max is 25 meters per second, which is not there in the option. So I think like it should be uh, we can double check this later on to find whether there is any problem with the options or not. So and then these pressure are given. So we actually don't need the pressure. That's what I was thinking. That's why I had solved using this problem. Are you like following me? It would be good if like if in the interaction is there.
Yes, sir. Following, sir.
Yeah. Mm, that's why I had used this conservation of mass. Okay. So conservation of mass should give me the answer itself. So since there is whatever fluid is going inside will come out as well. That's what conservation of mass ensures. So with that, I am getting my Vmax as 2 into V, which is 25 meter per second. If there is any like calculation mistake, that like please like let me know. But I couldn't find any. So what I am getting is this 25 meter per second. Now, the next portion of this problem is actually to find out what force is acting on this ball. There, actually, I have to use the conservation of momentum. Because what is happening to this fluid? What this fluid is means in this fluid box, there will be a pressure acting here. This is P1. There is a pressure acting this side. This is P2, which is given. This is given as this gauge pressure using H2O. So H2O gauge pressure is, I can find it out using my H2O density, H2O G into H. And again this P2 also I can find out, this H is given. So I can calculate that. So these two forces are there. And another force which is there is the one that is exerted on the this uh, ball. So since the water is hitting this, uh, there will be a drag force experience on this ball, and this ball will exert a force in the opposite direction. And this is the force that we need to find out. So this is a very typical wind tunnel experiment situation, where we are testing something in the wind tunnel, how much drag it will experience. So what we do is put that object in the wind tunnel, uh, uh, make a flow field across my wheel tunnel. I can like find the flow field at the exit, supply my flow field at the inlet, and from there, using these Reynolds transport theorems, we can find out the force that is acting on this object. Or like in experimental setup, there are pressure sensors which can definitely find the force exactly on the surfaces of this ball. So this is a typical wind tunnel setup. So this force is being asked. So for that we need to solve momentum. We will need to do momentum balance in extra. So here we have the temporal term, but the temporal term will not be there because it is not like this is a steady state. Again, this is steady state. Nothing is varying with time. So I will not write that. I will directly write my flux term. The flux term, this is this. Vx is there. We are only interested in x direction velocity. Vx is there. V dot in cap is there. Dx. This is equal to my forces. Yes, yes, sure. Is there any doubt?
No, sir. You please.
Okay, yeah. So the force which is acting on the x direction. So pressure forces I can like take the first surface. So P1 is definitely acting in the positive x direction. So P1 will be there multiplied by the area of one. Hmm. And P2 is there. It is opposite in direction. So P2, P2. And force is there. This F drag force is acting in the negative x direction. So minus F. So here also, like we have the first surface. In the first surface, integration rho Vx is inside, so this is the uniform velocity V, and V dot n is there. Since this is flux is getting inside the surface, we will have a negative sign. Normal n cap is directed outwards the surface, and V is inside the surface. The dot product will give us a negative sign. So this is a minus V square will be there, and dA. This dA will come out as a plus my second surface. So in this second surface, I have this rho, I will have this V square dy, and I will have this width, unit width. Again, this V square dy, our velocity profile is given. So from the velocity profile, I can integrate this and find out my expression for V square dy. This is equal to P1 minus P2 A minus A. So this is what is basically asked. F is there. Of course, if I take it on one side, P1 minus P2 into A is there, plus this is there. So this is rho V square into A square minus rho into W into this V square dy is there. So V square dy, again, if I come back here, so if I now have to solve for V square dy, what will happen? So V, if from like above 0, V is basically a linear function. So this is y into V max divided by h by. The reason I this form, like I am writing like this, because when y is h by 2, uh, the, this V is V max, and y is 0, this is 0. So if I write it like this, then I can easily like see the function. So 4 into V max square divided by h square, this will come out. Of this V square, so I am solving for integration V square. So V square I have put it here. So 4 Vm square by h square, this is coming out. What is remaining is y square. This is from 0 to h by 2. So I am solving only for the upper part. Why? Because the lower part is symmetrical. If I just multiply this answer by 2, I will get the lower part. This is y cube by 3. So y cube means h cube by 8. H cube, yes, h cube by 8. And 3 is there, so h cube by 24. So 4 and 24 is at the bottom. So 4 and 24 will cancel and give me 6. So this becomes Vm square into h by 6. This will be equal to 6. Please like confirm like, if there is any calculation mistake.
Sir, may I know how we can arrive at this Pm square h by 6? We are integrating V square dy,
Yes.
and in the place of V square,
Hmm.
we are substituting 4 Vm square by h square, no, sir?
Yes. Yes.
This one, how
So
we
in
are.
V, I am writing here. So V is y V max by h by 2. This portion clear
Y into V max.
by h by 2.
Uh, Sir, here we have derived V dy as V max into h by 2 based on this triangle we considered, and since we
Hmm.
integrated from 0 to h, we
Hmm.
multiplied by 2 into half bh V max into h by 2. We
Yes.
arrived V max into h by 2. Correct, no, sir?
Yes.
So
Correct.
So here we have arrived integral v dy as v max into h by 2.
Yes.
So now here we are multiplying v max by h by 2 by y, sir.
Uh, so here this is integration of this whole thing. So here also, if you put this y vmax by h by 2, you will see you are getting the same answer. There is, like, I did this as a substitute. Then, like, we can also find the area.
Ah, okay, sir.
Hmm. So if I just find the area inside the curve, then also this is similar to my integration. That's why I did half Vmax into h by 2. So Vmax and h by 2 are like the sides of the triangle, and half into the
O-
sides of the triangle, product of sides and triangle will give me the area of the triangle. This I can
Okay,
do
sir.
when I'm calculating v dy, because v is my function which is given, and dy is like v dy is straightforward integration. But here I am not integrating v dy, I am integrating v square dy. So when I am integrating v square dy, uh, this uh, this it is a squared, so this is not no more a triangle. It's no more a simple triangle. It is a uh, degree 2 polynomial. So like it's a degree 2 function. So y square is there. So it's no more a triangle. So that's why I can not simply use my formula of triangle area to solve this integration. So I need to know what how my v varies with y to integrate. So let me use a fresh page. This wait a second. I will prepare a fresh page. Yes. So uh, I will again like draw this figure. So this is y direction. This is h by 2. This is Vmax. So Vmax is the value of the velocity, right?
Yes, sir.
Mm, This is, so I'm not writing the negative term at all, because negative is like same. It's symmetrical. Hmm. So
Yes, sir.
whenever I'm integrating, I will simply multiply it with 2. Now I need to find what my v vary, like v as a function of my y. Okay. I need to find out how v varies with y. Otherwise, I will not be able to integrate. So since I know that this is linear, so this will be y into something, hmm, y into something plus c maybe. So plus c won't be there because I already know at 0 velocity is 0. So if at 0 velocity is 0, it is simply y into something. Okay, is that clear?
Yes, sir. Clear, clear, sir. V as a function of y,
Hmm.
we have to
Okay.
find out.
Yes. Now, at 0, this is 0. So this will be something multiplied by y. At again at h by 2, it is Vmax. So if I simply divide h by 2 and put Vmax here, then you can see that this satisfies this term. So if you put y is equal to 0, I get velocity 0, which is there. If I put y is equal to h by 2, I get my velocity as Vmax, which is also good. So this satisfies, right?
Yes, sir.
Hmm. Now, in the first case, I needed to find out this v dy integration from 0 to h by 2. I put this expression here. If I put this expression here, I can, since Vmax and h and 2 uh, these are constants, I will take it up.
Okay, sir.
Hmm. I simply have this 0 to h by 2, and I can, this is y square by 2 And if I put the limits, then it becomes h square by 4. This is h square by 4. So I simply have V max into h by 4. You can see that this is exactly same as when we did with this triangle formula. So in this
Yes, sir.
triangle formula, we obtained this, and we have got it here. I use the triangle just for simplification purposes. Now, in this case, right now, for momentum case, I need to find this v square dy. So v square dy, I will simply put this square of this. So if I put the square of this, then I will get 4 v max square by h square into y square. This is my v square, right? The square of this term dy. Is that clear?
Yes, sir.
Hmm. Okay. So this is 4 v max square by x square. Uh, this is y square dy, which will be y cube by 3. If I put the limits, y cube by 3, this will become h cube by 24, right? H cube by 24. Why 24? Because y cube by 3 is there, so this will be 3 into 8. 8 is coming as 2 cube. 2 cube is 8. So this is 24. So if I do my cancelling, like if I cancel terms which are, I am left with v max square into h divided by 6. Is that clear?
Yes, sir.
Hmm. Okay.
Clear, sir.
Yeah. So here we can simply put that uh, we are solving this side. If I have taken out one side, pressure difference, this is a force, it's there. Rho V square A, this is for the inlet term that is there, and rho W is there, and along with that will be V max square, V max square H by 6. So W into H is again area. So this area will definitely be there. There will be an area here, area term. Mm, these are the other terms. P1 minus P2 plus rho V square minus rho V max square by 6. So if I put these expressions, I will get one of these values. This, all the values for this I know already. It is mentioned. Every value is mentioned. Right.
Yes, sir.
Okay. Every value is mentioned. I can find out the force. All right. Let's move to the next question then. Yeah. So
Sir, one small doubt.
definitely.
Sir, one small doubt, sir.
Mhm.
Sir,
Yes.
in the previous question, why we subtracted that F, sir? Uh, when we wrote the momentum equation, we wrote on the right hand side P1 minus P2 into A minus F we put, no, sir.
Yes.
That F is the drag force, no? Why
Yes.
we are we have accounted it as minus F? Because its direction is in the direction opposite to the motion of the fluid. That is the
Mm,
reason, sir.
yes. That is correct. Hmm. So
Okay, sir.
this wall is there. So what we are concerned with, what this wall is, the force the wall is applied on the fluid, because we are analyzing the fluid. Hmm. So
Fluid. Okay, sir.
that is in this direction, and this is opposite to our positive x direction that we have. That's why minus. We can
Okay, sir.
also,
Okay.
yeah. Okay. Let's see this question. A free jet of water with a constant cross-section area A is deflected by a hinged plate of length L and supported by a spring with spring constant K and uncompressed length X. Find the deflection angle theta as a function of jet speed. Okay. So uh, the situation is like very clear here. So this hinge is there. It is a like free moving hinge, and jet water is supplied in this direction. It is going up and uh, like deflecting and moving upward in the upward direction. And this deflection, due to this deflection, there is a force that is acting on this plate, and a component of this force is used to compress the spring. So what we have to do is find this theta as a function of my velocity. So if my velocity changes, if the velocity increases, the compression will be more. So this theta will become less. So this we have to express mathematically how much it will be. We have to estimate this, and we can do it again using our Reynolds transport theorem. So here we will again consider a volume, control volume. So we will move along this jet and take two cuts, one along uh, this surface, outlet surface, one along the inlet surface. So let's say this is one, this is two. Here it's free jet, and so this jet inlet and outlet speed, we can consider both as our v, and here also it is said that the cross sectional area is A. So cross sectional area is A. So if it is a constant cross sectional area, so this jet cross sectional area is constant. So then we can definitely consider this as V as well. Why? Because if the cross sectional area is constant, our this V1 A1 which will is entering, so rho also will be there. So this is for our mass conservation equation. So this minus V2 A2. So if my cross sectional area is same, A are same, then my V's must also be same, because summation of these two will be equal to 0. So this V is same, that we can assume straight away. And now what we have to do? We have to solve for momentum conservation. We have to do momentum conservation. So let's draw this again, our control volume. So the two forces due to the flux will definitely be there. Here it is incurring with a velocity v, and here it is exceeding with a velocity v. And this plate, the unhinged plate, this will apply a force, and this force will be in the normal direction. So if I consider a frictionless force, we have already done a problem very similar to this, where we neglect the tangential force along the plate. By assuming the flow of the water to be frictionless. So if it is a frictionless flow, there is no tangential forces which is acting along the interface between the solid and the jet. So only the normal forces will be considered, and if it is only the normal forces, all the force that is exchanged between the solid plate and the water, that will be in this direction. So this F force, let's say, has been applied in this. So what we will take as my coordinate system to facilitate this, we will take this as one coordinate system. I need to find F. Okay, so that is my aim here. In our previous problem, we did not need to find f, so we like consider like this x direction, but here we need to find f. We will focus more on this y direction. So uh, let's solve this then. So here in my momentum conservation equation, I will have rho into Vy. Okay, we can also do one thing. We can, since yes, so one problem may arise that we need to talk about here. Like since this is deflecting here, and there is this this portion where forces might be exchanged in this particular direction. So we know that this is all the forces that is coming from this plate is in the normal direction of this plate. What we will do is let's do one thing. Let's divide this into two components. And instead of using this coordinate system, so we can also use a more conventional coordinate system, just simply align in the vertical and the horizontal directions. So f is broken down into two components, fx and fy. Now fx, for fx we know only this fx is responsible for all horizontal directions. So the reason we can like do this, this is more uh, favorable than the one we were proceeding right now, just now, is because there will might be some vertical forces due to the ground here, hmm, which also has which also may act and provide some additional forces. And like this, since this hinge is also there, so there might be some extra forces from the ground that might be affecting the fluid. So let's neglect all this and let's only consider the horizontal force. So no ground effects will be there in the horizontal direction. So I will change this. If there is any question, please feel free to ask. This will be equal to minus x because it is acting in the opposite direction. So minus x. So let's break this down. So this is surface 1, this is surface 2. So for surface 1, this rho Vx, this is positive Vx, so V, and V dot n, this is going inside, so this there will be a negative sign. And the area is constant, which is A. Uh, So this is for the first surface. The second surface, what would happen? Rho Vx. So Vx here will be component. So it will be V cos theta. And V dot n, this is simply V, and it will be in positive direction because it is moving outwards of the control volume. So this dot product will leave a positive sign. And dA integration will give this. This is equal to minus x. So my x direction force is simply rho v square a 1 minus this is my fx. Okay, so which is my theta? My theta is this. So if this is fx, how much will be fy? How much will be f? Now let me just draw the free body diagram of the hinge. The hinge here. So this is like this means plate which is attached to the hinge. So Fx I know, which is the component of along this x direction. So what I need to find out now is this F. So can you tell me how much that will be? If I know Fx, what will be F? And this is theta. If this is theta, then this will be theta. So this F will simply be Fx divided by sin theta, right? So this will be Fx divided by sin theta. So F will be rho v square a 1 minus cos theta divided by sin theta. Now we are not even asked that. What we are asked here is uh, is like to relate it with the spring. So we have to relate this with the spring. And since there is a hinge here, what we like need to do is basically uh, make a angular momentum like balance, torque balance about the hinge. So hinge some x and y forces they will be there, and here is the figure drawn. You can see that the spring is acting this side, this way. Spring is acting this way, and this is theta. So uncompressed length x0 and x0 is my uncompressed length. So this is given here. So I do not know the center of pressure. This plate of length L is supported by spring with spring constant and uncompressed length x0. What I can like simply assume here is like let's say this F is acting on this hinge. So it's acting somewhere here, and uh, the what I can assume it's let's say it's acting at half the length. So like center of pressure is like it's not given. So we can assume it to be a geometrical. If we assume it to be the geometrical center, then we can uh, put this F into L by 2. Let me write it here. F into L by 2. This will be equal to uh, this force due to this. This will be x minus x naught. K into x minus x naught. Uh, into, so this is L cos theta. L cos theta. So if I put this expression here and separate out theta, yeah, please let me know if there is any difficulty.
Yes, sir. May I request you to clarify how we are writing f L by 2 is equal to k into x minus x naught into L cos theta. No, sir. That how we are arriving at, sir. Which is x minus x naught.
Yeah. So here our uncompressed length is given as x naught. Hmm.
X naught. Yes, sir. Yes.
Yes. So if it is compressed by like length x, if the spring is compressed by length x, so the difference x
Okay.
minus yeah, x naught.
X minus x naught will be then negative. No, sir.
Oh, okay. Yeah. Sure. Sure. Wait, and in fact, x is not given here. So I think we can approach it in a different way. I think we can approach it in a different way. Hmm. You're right to point out that. Hmm. Thanks.
Yes,
So x naught is the uncompressed length. Hmm. So
yes, sir.
x naught is the uncompressed length. So the force that will be applied then, if I want to take the positive value, will be x naught by minus x, right?
Yes, sir.
X naught minus x. X naught minus x. So k into x naught minus x to L cos theta. So this should be uh, so I
L
have
cos theta. Yes, sir. L cos theta is this x direction side, sir.
yes, L cos theta will be this length. L cos theta will be
This
this.
length. This
This is
length.
L cos theta. This is it.
Okay.
Since it is not give x is not given, I think we can also like assume that this they want this like length to be x. Hmm. So x you can also I think replace with L sin. Then there is actually no like unknown here. You can means only unknowns will be v and this theta. Hmm. So theta you will be able to get in terms of the v, right? Because x is not given here. X is not given here. So x I can put it in that. X I can put as L sin.
So L by 2, why we are dividing it by 2, sir? F L by 2.
Hmm.
So we are
That I have made an assumption here that the like since uh, we had calculated the amount of force that will be exerted by the plate on the fluid volume, but I do not know exactly at which point that force will be acting.
okay, sir.
Right? Hmm. So what I have assumed that this is our center of pressure that we had uh, like, means studied in some previous lessons. So center of pressure
Okay,
is where the fluid acts at which point that force acts. So that I am assuming it to be in the geometrical center, which
okay,
is
sir.
an assumption, but a reasonable. So if it's at the geometrical center, then I can take F into L by 2 as my torque about the hinge.
Okay.
Mm. Should I proceed to the next question?
Yes, sir. Sir, you may kindly proceed. So now, if we can find out theta, actually it is coming. Which option it is coming to us, sir? Which option? Theta.
This option has been given. So I guess it will not be very straightforward to separate out theta because of these terms, 1 minus cos theta. Uh, so uh, with a little bit of exercise, this option A is marked as the correct one. If there is any
Okay.
so um, I will have two sessions are actually remaining, so we will do one session on Thursday. So if there
Okay,
is
sir.
any problem there, in this obtaining some answers, like we can discuss it there. And also one additional session as a like a summary and doubt clearing session will be done in the next Tuesday in this time. Hmm. So,
Okay, sir.
so there also we can discuss any like leftover questions or doubts that we have, that
Okay.
we can discuss. And like you can uh, put it the doubts you can put it in the these are uploaded in the YouTube, so you can put it in the YouTube comments. I can read it from there. So before the like class, I can then means, like prepare the solution so we can do it very quickly in our session. If you have like any problem, then you can mention it there. I can like directly read it from the comments. Okay.
Okay, sir.
So the next question is a large tank of height 1 meter and diameter is uh, fixed to a cart as shown. Water issues from the tank through a nozzle of diameter d. The speed of the liquid leaving the tank is given, where y is the height from the nozzle to the free surface. Determine the tension in the wire as a function of y. So this is also like a straightforward Reynolds transport theorem question. So here the force is basically acting due to this water leaving this reservoir. So due to the water leaving this reservoir, some force will be acting. So how can we find out how much force is acting? We can simply put this force as our flux through this surface. So only one surface is there in this x direction. So there definitely this water level is coming down. So there is some flux to that, but that is in the vertical direction. And so in the x component, it won't. This won't mm, like, have any component. So x direction we are considering. So here rho vx v dot in here d. So area of the nozzle, so the diameter of the nozzle is given as d. Hmm. So first of all, rho will come out. Vx is given as root over 2gy. So, so this is Vx first of all is positive, and V dot n cap here is positive again because it is leaving the control volume. So control volume is this reservoir, not drawn. So this is the reservoir. It can be taken as my control. So V dot n will also be positive. So it will be V square. So V square means 2G into Y. And area is D is given, so area is pi D square by 4. So this is my force. That is mm, uh, force due to this water that is coming out of the nozzle. So if I like draw this diagram again, so it is over this part. So if this force is there, this force, uh, its x direction force. This is acting on the fluid. Hmm. So this is an x direction force which is acting on the fluid uh, via this flux, and if it is acting on the fluid, this fluid is acting like giving some force to the this cart. So this cart, the fluid is giving force in this direction, positive direction, negative direction. So on the fluid, due to the flux coming outside, of positive positive x direction force is supplied on the fluid, and this then again this fluid then applies a negative x direction force on the cart. So this F is applied. But this cart is fixed. Cart is not moving anywhere. Why? Because a wire is there which is applying a tension force T. So this F will be equal to T, and which is equal to this is the, just now we calculated. This is rho g pi d square by 2. This is rho g pi d square by 2. Okay, and y is there. Definitely y is there. Rho g pi d square y by 2. Okay. Is there any is this understood how this problem is solved? It's one of the simpler ones. We'll move to the next one. Yep. Okay. So a water jet issuing from a stationary nozzle with a velocity v is given, jet area is given, and strikes a vane mounted on a cart. So this is again like turning this water jet and like deflecting this water jet, and that's why some force is being exerted. Uh, so that force is again balanced here with this weight. So this mg is there. It is counteracting this cart, and what we have to find out is the value of this m. So, so here we can like first draw this jet. So this jet will be exiting like this, entering like this. So we can again draw our control volume for applying the Reynolds transport theorem. Now again here the inlet point is 1, this outlet point is 2. Whatever our atmospheric pressure is there, it is acting on all surfaces, so integrating that will be 0. So the only forces that are acting is from the flux of 1 and 2 and the force on the cart. So, and this cart force, we are what we are more interested in. We are interested in this tension force, right? This tension force that is acting on the cart. So, this tension force, this is basically balanced by the force applied by this fluid on this x direction. So, this Fx is what we are trying to calculate, and this Fx in turn, this cart is actually applying this Fx on this fluid, on this jet in the negative direction. So, this will actually be in the negative direction. So let's calculate that. So here again this term, this flux term Vx is V dot n cap dA. This is equal to minus X. So the exit velocity and area is actually here not said, but we need this to calculate our to calculate this. So what we will assume is, since there is no tangential forces, it is told to neglect friction between the uh, cart and the road, and like we can also like neglect any friction between the jet and the cart. So it is a, if we assume it to be a frictionless force, frictionless flow, then again the outlet velocity this will be v, and if the outlet velocity is v, this area will also be the same due to the continuity. So due to continuity, the like area in the exit will be same as the area of the inlet. So in this way, we will now like solve this. So in the first inlet, it is rho, Vx is positive V, and V dot n is negative V minus V. This is minus V square. A is there. For the outlet, so this is rho. Vx is V into cos theta, and V dot n is positive V. So this is plus V square, and area is there, A is there. This is equal to minus Fx. So this minus Fx uh, is so this Fx is what we needed to find out. So this is rho V square A and 1 minus cos theta. And this Fx is basically my T tension, which is holding this, and this tension is equal to the mg. This is the weight uh, which is holding this cart. So the m that is required here is basically rho v square a divided by g into 1 minus. So all the values are given already. So we can like simply put the values and find out what the answer will
Sir, excuse me,
be.
sir,
Yes.
one small
Yes.
doubt. Why we are considering here as minus fx, sir? Because that fx cot that is along the x direction only, no, sir. Well,
Yes.
then why? Only the tension is in the opposite of x direction. T is in the opposite of x,
So
isn't it?
let's like uh, break it down. So this is, let's say, the jet.
Yes, sir.
So this is the water. So here this is entering and leaving. So this is basically the control volume.
Yes, sir.
So forces are being applied due to these fluxes, and uh, can you see the screen?
Yes, sir. I can see.
Uh, is it visible?
Yes, sir.
Yes, it's
Visible,
visible.
sir. Visible.
Yeah, okay.
Visible, sir.
Yeah. So this is the jet, and on this jet, on this water surface, there will be a force which is applied by this cart in the x direction. And this cart is there, which is another body, a separate body. This on this cart, there is force which is supplied by this water body as Fx on this cart, and
Yes, sir.
there is also a supplied tension which is T. And again, this tension is carried over through this wire, and this tension is supplied on this mass M, uh, and on this M also there is another force mg. So we have a lot of balance here. First of all, here we have this flux term. This is equal to my fx. So here minus fx will be there because it is in the minus gate. Right? It's in the
Yes, sir.
opposite direction. And here again this fx here is in the positive direction. Minus t, this will be equal to 0. And here again this t minus mg. This is in the y direction. T is positive y and mg is in the negative. So these are three separate bodies. One is this mass, one is this cart, and another is this jet. So on this cart, Fx is applying on the positive x direction, but on the water, on which we are actually applying the Reynolds transport theorem, it is the Fx is applied on the negative x.
Yes, sir.
So let's move to the next question. So a rectangular block of mass m with vertical face rolls without resistance along a smooth horizontal plane as shown. The block travels initially at the speed u0. At t0, the block is struck by a liquid jet and speed becomes too slow. Obtain an algebraic expression for the acceleration of the block at t greater than 0. So at t greater than 0, what happens basically is the jet is striking this. So this mm, so mm, the jet is basically striking this mass and it is spilling, and along this x direction there will be no relative velocity between the mass and the jet. Is that clear?
Along x direction, there will be no relative motion between the
Mass
mass
and the jet after it hits. So after the jet hits it, so it is like basically spraying a jet on a wall. So it cannot cross the wall. So at the wall,
yes,
the relative velocity between the wall and the jet will be zero. So that is
yes,
what
sir.
will
Yes,
happen here. So in
correct,
this
sir.
case, we need to be very careful about the relative velocity. So what we mean, like at this point, there will be no relative velocity between the mass and the jet, but still there will be a velocity of the jet which will be equal to u. Correct?
Yes, sir.
U is the velocity by which the mass is moving. So here we will again apply our Reynolds transport theorem. But what we will do is sit on the top of the mass. So we will look on the reference frame of the mass, so that this confusion, like so that this confusion does not arise. So what will happen basically? If we are sitting on top of the mass, then there is a jet which is uh, coming with a velocity v minus u, v plus u, because v is in this direction and u is in this direction. So this will be v plus u, right? The velocity of the jet.
Yes, sir.
Hmm. And at this surfaces, those velocities will like move in the y direction, and the x direction there is no outlet. So whatever the velocity is there, it is like spilling over in the y directions. There is no x velocity, like x direction outlet. Hmm. So that is there. So our control volume is something like this. This is my surface one, and this is my surface two. These are the important surfaces. Why? For the x direction momentum, because the other surfaces are not contributing anything in the x direction. So, like if I do my momentum equation here, for this surface one, it is rho. What we had integration rho vx into v dot n cap d, right? So we have
Yes,
rho, which is constant. Vx in this case is minus minus v plus u. This there is a minus here, and v dot n cap. So since this is entering inside, there will be another minus. So this minus and minus will become plus. Hmm. So and this will also be v plus. So this is v square into a. A is the area of the nozzle. A is the area of the nozzle. So this will be equal to F. What is F? F is the force that is applied on the mass. So this is there. This is my Reynolds transport theorem in this case, using
yes,
my
sir.
relative velocity. Now what is this F? This is F is acting on the mass. So if I draw the mass, there is F acting this way. So this F we know is what is slowing this like body of mass down. So this F will be equal to m du dt. and there will be a minus sign. Why minus sign? Because this is slowing it. This is a deceleration, so there will be a minus sign. So I will simply put this here. So this is minus m du dt. So if we rearrange this, then du dt, this becomes minus rho v plus u square a divided by m. As you can see, this is the last option. So that is the correct answer. So we have to use this like concept of relative velocity in this case. So we have not applied our Reynolds theorem here directly in the reference frame we are looking. We have transferred our reference frame to the mass reference frame, and on that mass reference frame we have applied our Reynolds transport theorem to get the correct
Uh,
answer.
Sir, one small doubt.
Yes,
This rho, the relative velocity is v plus u. The meaning that is minus v minus u only will come, no, sir. Minus v plus uh, because v is in the opposite to x direction, so it is
yes.
minus v. Correct, no, sir? And minus v minus u.
I understand
So
what you are saying. So you are saying minus v
so
minus
minus,
u.
yes, sir. So minus of v plus u
Hmm.
into minus of v plus u. That's how we get v plus u whole square, sir.
Yes, that's correct. That is correct.
Okay, sir. And
Hmm.
equal to that, F is the force that is exerted by the
Mass on
control
the
volume, by the mass on the fluid control volume. Correct?
yes,
Fluid.
that is correct. That is
So,
correct.
so that F is in along the x direction, so it is positive.
Yes, that is correct.
And then how we get minus of minus m du dt?
Hmm.
That one how we
So that we have to now not consider the mass, the fluid control volume. Now we are considering the mass. So this m
mass
on
here.
this m, the force is
Okay, sir.
applied on the negative x direction, right?
By the fluid on the mass.
Yes, fluid on the mass, negative
Okay.
direction for forces applied. So if you just not think about deceleration and acceleration, just simply write blindly. If we also write m du dt,
Okay.
then this will
M
be
du
equal to
dt.
minus f because the direction is in the negative x direction.
Okay, sir.
So
Okay.
that's why this
Okay, sir.
minus sign is
Got it, sir. Got it.
here.
Thank you, sir.
Okay. So here it is referring to the previous problem. Hmm. So in this previous problem, they are asking at which time the our velocity will become zero. So what is happening basically? This mass is has a initial velocity, and this jet is slowing it down. After some time, when it has slowed it down enough, it will reach velocity zero. And then because this jet is continuing to apply force, it will actually start moving in the opposite direction because of the jet. Hmm. So what is it is asking is when this will happen? When will my the turn it will start moving in the opposite direction, or when my velocity will actually reach zero? So initial speed is given as u0. This is important. At t is equal to 0, my velocity is u0. So this will be helpful for us when we put the initial condition. So we already have our expression of du dt. So du dt expression is here minus rho v plus u whole square a by m. So this is minus rho v plus u whole square a by m. Yes. So we can simply do this integration. So du divided by v plus u whole square. So this is the u term. Hmm. The other are constants basically. We can keep it here. And we will integrate both of them. So if we integrate this, so we will get uh, minus 1 by v plus u, and if I integrate this, I will get rho a m into t, and I will get an integration constant c. Now I will put my initial condition t0 at t0, u is equal to u0. So if I put t0 and u is equal to u0, I simply get c as c equal to minus 1 by v plus u0. Is that correct?
Yes, sir.
Hmm. So now what is asked? I am asked the time when u is equal to 0. Hmm. So I will keep my time as t and put u equal to 0. Hmm. So let me do it in the next. Let me do it in the side. So if I put this as 0, this will be minus v, this will be minus rho a m into t, and this is minus v plus u. So I will get v equals v plus u0, u0, and rho a. Here I will get this is equal to 2. You can check whether this is uh, the calculation is correct.
Okay. Okay, sir. This is okay, sir.
Hmm. So this is the general pattern. So these are very important questions in fluid mechanics. The application of Reynolds transport theorem. So mm, like this was the last question. So but a lot of problems, similar type of problems will be there in the textbooks, whichever textbooks you are following. And I would recommend doing that because like solving these problems accurately requires some amount of practice. If there is any problem that is like specifically means, there is some problem solving it, we may you may bring it to my notice. I will try to address that. So we will have like two more sessions that, as I like previously said, one on this Thursday that will be like informed to you, and another on Tuesday, which will be the final session, where we can like discuss the doubts.
Okay, sir.
Thanks for joining. Have a
Thank you
nice
very much,
day.
sir. Thank you.